Joe Stagg, and I'm with Pipeline Development Company. Together, partnered with Patterson Pump Company, we are bringing you a two-part webinar series providing training on centrifugal pumps for the HVAC application. Patterson Pump Company approached us and asked us to put together some training material for their equipment manufacturers, for their mechanical engineers and their mechanical contractors, anybody who uses their centrifugal pumps in HVAC applications. Their goal, our goal, is to help educate the industry, and we'd like to provide this training to those in particular who use Patterson pumps. In this two-part webinar series, each webinar is about an hour in length. The webinars, we're going to start with the very basics of what a centrifugal pump is and how a centrifugal pump works in a closed loop and open loop hydronic system. By the end of the second hour, we'll be getting into more technical components where we apply VFDs to pumping systems. Now please understand that Pipeline Development Company, we're in the training business. We teach lots of different HVAC applications, how to properly size and select equipment, and we do this all across North America. We teach lots of different seminars. We also do a lot of online training for all of our online users. If you visit our website at www.pipelinedevco.com, you can find all sorts of different webinars. We're always putting out new training webinars, anything revolving around HVAC systems, from pumps to boilers to chillers to cooling towers to fan coil unit systems to whatever it might be. We are here to assist the HVAC professional with designing, installing, operating, and maintaining their systems as efficiently as they can. So in this 2 hours, we really want to help you understand centrifugal pumping systems and how you can make them work a little bit better. Now, we really believe that with knowledge comes power. So the more you know about this, the more you can utilize that in making a more efficient system. In this first series, in this first webinar, we'd like to start off with explaining how we move flow throughout a system. We'd also like to get into what a centrifugal pump is and how it works and how it operates. We'd like to then get into selecting some different pumps. And when we select the pumps, I'd like to take you to Patterson Pump's website and use their selection software. We'll also look at a Patterson Pump curve and understand all the components that are on that curve. So as I said, with this first webinar, we're really going over the basics. We want to make sure that you understand the ins and outs of selecting a pump, and we'll show you how to do that using Patterson Pump's website. So first of all, when we talk about moving water through a system, well, I assume that most everybody who's watching this webinar deals with HVAC comfort heating and cooling systems. We're in the business to provide comfort to the occupants of our buildings in our area. So what is it that we need to pay attention to? As we provide comfort, we can look at high efficiency, but one of the things I really stress is our first priority as HVAC professionals is to provide comfort to our occupants. If they are not comfortable, it doesn't matter how much money I spent on trying to be efficient. We simply are not efficient. I could have designed all sorts of control algorithms. I could have used very expensive components like condensing boilers, variable volume chillers, whatever it might be. I could spend a lot of money on this stuff, but at the end of the day, if my building occupants are not comfortable, then I simply have failed to do my job. My first priority is to provide comfort. So when we look at a comfort heating cooling system, more often than not, unless we get into the condenser water system, we've got a closed loop application. So I've got a piping system that's closed and sealed from the atmosphere. Now, we're not going to spend a lot of time defining what that is. We simply do not have time in these 2 hours. But in this closed loop system, it's sealed off from the environment. We might have to lift up 3 stories in a building. But what I have to lift that water, I also have the weight of that water back down in this closed loop system. So when we size a pump or when we put something in here to move the water, I don't have to move that water up because that water is moving itself down. So when I want to move flow, In a hydronic heating or cooling system, we're using water or a liquid, maybe it's a propylene glycol solution or some type of water solution that we're going to heat and cool this building. And we need to move the water out to this building so that we can get it out to maybe it's a heating coil, maybe it's a fan coil unit system with a cooling coil inside of it. Maybe this is an air handling unit with a cooling coil inside of the air handling unit. My goal or my objective is to move the water throughout this loop and back so that I can either heat it back up or cool it back down. We're moving that water out to the system components so that we can have heat transfer and provide comfort to our building occupants. Well, how do we do that? Too many HVAC professionals that I've worked with have told me, well, we use centrifugal pumps because centrifugal pumps move water. Now, I'm here to tell you that's not what happens, and we're going to go over the basics. A pump is not put in this system to give you a flow rate. Let's say in this system, I needed a flow rate of 150 gallons per minute, GPM. If I want 150 gallons per minute, I put a pump in to do that. But that pump is extremely stupid. It's got no intelligence. It's not going to say, okay, give me 150 gallons per minute. All it's going to do is rotate. So how do I get flow to move through a system? What creates flow? What it really boils down to is a change in pressure. If I want to move air through my ductwork, I have to change the pressure. When we have wind blowing outside, it's because we have changes in pressure. A change in pressure will create flow. So I've got to create from point A to point B. If I want to move water in this direction, then I've got to change the pressure. We always have a flow from a low pressure or a high pressure to a low pressure. So if I have a higher pressure here and a lower pressure here, then I will have flow in this direction. So that's what we're trying to accomplish in a hydronic heating or cooling system, is create a change in pressure between these 2 points so that my liquid will move in the direction that I want it to move in. Well, how do we do that? How do we change the pressure? Let's say that I have a can of water, and we put some water in here, and I punch a couple of holes in the bottom, and we open this to the atmosphere. What is going to happen? Precisely, we're going to have water flowing out of these holes, and my water is going to drain. But now, this water is only maybe spilling out to the front tables here. If I want to get those of you in the back of the classroom wet, how do I do that? This water is not flowing out very fast. I don't have a lot of velocity. I don't have a lot of distance. But I want to get you wet out there. How do I do that? Well, I need to change the pressure. I need to increase the pressure inside of this can, or increase the pressure at these points. Well, how do I do that? There's a couple of ways that we can address this. First of all, we have to understand that 1 psi is equal to 2.31 feet of water at 60 degrees Fahrenheit. So if my water is at an elevation of 2.31 feet, then I have 1 psi of pressure. Well, if I want to increase that pressure, well, then it makes sense to maybe elevate that water column. Instead of 2.31 feet, let's lift it up here to 5 feet. Now I have almost 2 psi. Now I'm not getting those of you in the back of the classroom wet yet, but I am getting you in the middle wet. So I've increased the pressure by elevating my water column. Another option is I could seal this can from the atmosphere, and I could provide it a motive force, a motive pressure, maybe compressed air. We do this with steam in condensate return applications. We provide something that's at a higher pressure. We could provide a 20 psi motive pressure, and suddenly I've got a lot of pressure, and now I'm getting everybody in the room wet because I'm really pumping that down or pushing it down with the pressure. Well, this is a great example of what a pump, a centrifugal pump, is going to work. If we eliminate these options and I mount this can on a rotating assembly, I now move this in a centrifugal motion. I spin it. If I were to look down on the can, I'm moving the can in this direction. I'm rotating it. All of my water wants to spin out to the edges and will begin to create more pressure. I've got a lower pressure in the middle, and I've got a much higher pressure towards the outer edges of that can. If I were to rotate this can, the faster I rotate it, the faster I spin it, the more pressure I'm going to have, and the further my water will spin out of that can. So what I'm doing is I'm rotating this in a centrifugal motion. So let's talk about centrifugal motion. Now, I had a professor years ago tell me that there is no such thing as centrifugal force. Now, some will contend that, some will argue that. But what he said, or how he explained it, is that centrifugal force is really a byproduct of centripetal force. So that we all understand what I'm talking about, let's discuss centripetal force. If I had a pole, and I'm looking down on this pole mounted into the ground, if I had a pole and we attached a tether line to that pole, and then we mounted or attached a ball to the end of that tether, I extend this tether so that the ball is at its full extension, and I push the ball in a direction. Well, based on inertia, that ball is going to want to continue moving in that direction. However, this tether tied back to the center point does not allow that ball to move in a straight direction. It drives that ball back to its center point. That is what we call a centripetal force. We are continually driving this ball back to its center point. However, because of the laws of inertia, this ball does not move to its center point. It now changes its location and tries to move in a straight line. But it's pulled back to its center point. So it changes its location and tries to move in a straight line. But it keeps being forced around and around and around. That force is actually pulling us back to the center point. But we don't feel that force. If we get on a merry-go-round and that merry-go-round spins faster and faster and faster, we don't feel that force pulling us back to the center point. We don't feel the centrifugal force. What we feel is what people call centrifugal force. Now, because we can argue that there is no such thing as centrifugal force, I call it centrifugal pressure. As I'm sitting on that merry-go-round, and that merry-go-round is moving faster and faster and faster and faster, I feel more and more pressure to get thrown from that merry-go-round. A great example, when we used to live up in the state of Washington, I used to take my little kids out to this park that had one of these little merry-go-rounds that had the little bars that came off, and the kids could hold on to these bars, and Dad would stand out here and spin this thing faster and faster and faster. As long as my child, or my son or daughter, as long as they were holding on to this and close around that center point, they were okay. But as Dad spun that faster and faster, they felt more and more pressure, and they started getting pulled out here. Once they moved away from the center point and they got out here and they were holding on, their legs were flopping out here and they were just flying around this merry-go-round. Why? Because the further away you get from this center point at the same rotating speed, the more pressure or force we are creating. And it's all because of this centripetal force. So hopefully we understand the difference between centripetal and centrifugal. We don't feel the centripetal, we feel the centrifugal pressure that we are experiencing as we are rotated around. So if I take this same mentality now, and we'll change colors here, and we take this can of water, and we fill water into this can, and I put this can of water inside of another can. But this can has an outlet so that I can direct. Yes, I'm spinning water. In this can, we're going to have some vanes in here to help distribute that water or to help move it to the edges of that can. And as we move it to the edge of that can, as it's rotating, that water enters that can and is then thrust from the internal can as we spin around and around. My water is being thrown around, but we're now directing that so the water then is able to exit in the direction that we want it to. We have a lower pressure versus a higher pressure. And that high pressure now creates flow through that system and then back. The centrifugal pump is creating that differential pressure simply by moving in a centrifugal motion. That moving in that motion creates that differential pressure because of this. Now, I get asked all the time, Joe, my pump is wired backwards. My pump is rotating backwards. My motor's spinning backwards. Am I going to now move flow in this direction? If my pump is wired backwards because I'm a three-phase motor, and so we simply cross the lines and now my motor's rotating backwards, my pump is spinning backwards, does that mean I'll now flow in the reverse direction? No, because it all comes back to centrifugal motion. I'm still moving in a centrifugal motion. If I spin this merry-go-round with my kids on it faster and faster, but then I stop and then spin it backwards, it doesn't suck them back into the middle. We still create that centrifugal pressure and still throw everybody off. We're just doing it in the reverse direction. So if I rotate a pump backwards, we're still going to have flow. But the problem is we don't know what that flow rate is because the manufacturer didn't give us the published curves of doing that. So we're not getting anywhere near the flow that we want. And we're going to talk about the components in this pump in just a little bit. But it's important that we understand that that's all this pump does. I speed if I were to speed this merry-go-round at 1,800 RPM, 1,800 revolutions per minute, as we rotate that, it's a constant pressure. My kids are going to be gone. They're going to be flown across the park. But if I do that here, and I keep that at a constant speed, then I'm going to build a constant pressure. What kind of flow rate am I going to get? Well, I don't know until I look at what the manufacturer tells me I can get. All this pump knows is that it's going to rotate at a given speed. That given speed will develop so much differential pressure, and based on that differential pressure through the system, we're going to develop so much flow rate. The pump is stupid. It doesn't know to give us this. All it does is rotates in that centrifugal motion. Okay. Before we move on to selecting pumps, I do want to talk about that impeller. Let's define these terms. If I have a can inside of a can, this external can would be considered my pump volute, or the pump body. The volute is hydraulically designed by the manufacturers. Patterson Pumps is going to design their hydraulic, the inside curvature and the roughness and everything else inside this is going to define how their pump is going to work compared to a competitor. So they designed this in their R&D, their research and development. While they're building a product, they're running this through the design. So they hydraulically designed this. They then add the second can inside of this pump, or inside of the volute, and this is what we would call the impeller. The water enters the eye of that impeller and then is rotated around or spun around. And as we rotate that, we create the differential pressure. These are called the vanes of the impeller. The impeller is also hydraulically designed. Very important how many vanes we have, how thick, if I were to look at the side view of this impeller, how thick is my impeller? And we're going to have the eye of the impeller out over here, and it's rotating on the shaft. Is it a thin impeller? Is it a thick impeller? Is it an open impeller? And we've got our vanes that are attached here. Is it a closed impeller? All of these will define what my pump curve looks like. So when we look at a manufacturer's pump curve, it's all based on these two components. It really has nothing to do with the motor. The motor is there to drive it. There's really three parts to most pumps. You've got the drive assembly, which is the motor, and the motor shaft. If you get into a split coupled type pump or a flexible coupled pump, you're going to have a bearing assembly with the pump shaft Again, it's still part of that drive assembly, but it's there to drive the impeller, to rotate the impeller inside of the volute. It's these two components that make up the pump curve. Everything else is there to support it, to drive it, and to create that pressure. If we have an open face impeller, you're going to have more. We see this in plumbing applications so that we can pass a 2-inch solid if we're using a pump in an effluent type system or some heavy wastewater type system. Typically in a closed loop hydronic system, we'll be using closed face impellers. But an open face impeller will typically give you a much flatter curve. Now we're going to talk about curves in just a minute, but it'll give you a flatter curve. A thin closed face impeller will give you a likelihood of more of a steeper curve. A fat impeller will also give you a more flat curve. So again, the design of this, whatever the manufacturer, whatever flow rates and pressures they're trying to get to, will define how they're going to design these components. This is why it can be very difficult to take a pump that's actually been manufactured for the agriculture business and use it in HVAC, because agriculture applications might not have the same flow and head or typical same flow and head conditions that we have in HVAC. I see engineers make a mistake when sizing their pumps or as they calculate the pressure through the system. It's usually pretty standard in a closed loop hydronic system. Because we don't have to lift the elevation, it doesn't matter how tall the building is. Really it matters how long our piping is and how many zones we have. So typically we're within a pretty good range. So all of your commercial HVAC pump manufacturers will have pumps that look fairly similar in their curves. Some will be more efficient than others because they've spent more time in their R&D. My personal experience of working with the different pump curves, I have been very impressed with the Patterson pump curves. They seem to be very efficient, a lot of times more so than the competition, and you know, they really know what they're doing. So you've got some good product that you're looking at, that you're using. But this is, again, what draws or what defines these pump curves. So now let's clean this up, and we'll start diving into more of the actual pump curve, how to read it, and how to understand everything that's taking place on that pump curve. Let's put up an actual pump curve from Patterson pumps that we can look at and analyze and understand everything that they're displaying on the pump curve. This is the Patterson pump model E2.5J7A-CC from their HVES series. It's a horizontal end suction closed coupled pump. The CC stands for the closed coupled. Now typically most manufacturers, whether it's closed coupled or whether it's flexible coupled, typically it's the same curve. Why? Because they're using an end suction pump. It's using the same volute. It's also using the same impeller. It's just that the drive assembly has changed. If we have a closed coupled pump, then I've got my motor, and on that motor shaft, typically we would use a JM motor frame. That JM motor frame tells us that we've got a special shaft because it has to be elongated. So that shaft is a little bit longer, and it's got a mounting bolt on the back of it so that we can mount the pump impeller to the motor shaft, directly to the motor shaft. This would be more of a direct-driven pump. And then you've got your pump housing around it, and so forth. We've got the mounting screw here. We've got our mechanical seal here. You then have your motor mounting plate here. But this would be a closed coupled pump. Well, I could take a flex coupled pump or a split coupled pump. I've got my T-frame motor, which is more standard off of anybody's shelf. We then have a coupling that couples the two shafts together. I've got my pump shaft with its bearing assembly here that it goes through, and then we've got our pump housing with the impeller mounted to that pump shaft. And then this is all mounted on a base with some supports here. It's the same volute and it's the same impeller. Therefore, my pump curves are probably going to look identical. All that's changed is this drive assembly from my flexible coupled pump or split coupled pump to my closed coupled pump. It's the same curves. So I've picked a closed coupled pump because of the size of my motor for this application. But let's just look at this curve. We've got a lot of different lines. First of all, let's look at the impeller trim. The impeller trim shows from 7 1/4 inch diameter down to 4 3/4 inch diameter. If I were to draw a similar pump curve up here on the board, and I've got my 7 1/4 down to, what did we have, the 4 3/4? This 7 1/4 is the largest impeller trim that I can have. The pump model is a E2.5J7A. That 7 designates, in the model number, that 7 designates the size of that volute. The volute cannot hold anything larger than a 7 1/4 inch can or impeller. If I put anything larger in there, it just won't fit. So this, what this is doing is I've got a 7 1/4 inch diameter can or impeller inside, and then I've got very narrow spaces between the two cans. So I can't fit an impeller any larger than that because I simply don't have the space. This is the largest impeller trim that I can use. As we get into efficiencies, I want you to understand, look at the distance between this wall and this wall. The distances are so small that as I rotate the water out of this can, there's no room for it to turbulate around. It just moves fluidly through here. So we're going to talk about that when we get into efficiencies. On the other side of the curve, down here at 4 3/4, this is the smallest can I can put inside, or the smallest impeller. So I take this same size volute, but now I've got a much smaller impeller. As I've trimmed the metal off of that, as I've made the diameter smaller and smaller, I've increased the gap size between these two walls so much that as my water spins out, it can turbulate around. And so my efficiencies in my pump are going to decrease. If I keep going and assume that I can put smaller and smaller impellers in here, that distance becomes so great, I've got such a small, it's rotating, but my water's just doing whatever it wants out here. It's not moving in the direction I want it to. That's why we have a maximum trim and a minimum trim. And most manufacturers will give you a 1/8 inch increment. So looking back at their curve, they only show 1, 2, 3 impeller trims. They show 4 3/4, 5 7/8, and 7 1/4. You don't have to assume that you have to use one of those 3. Like I said, most manufacturers will trim their impellers to increments of 1/8 of an inch. So we could go from 4 3/4 all the way to 7 1/4 in 1/8 inch increments. So that's how we read the impeller trims. The next I've alluded to are your efficiency curves. So let's take a different color here, and my efficiency curves will look like this. They're dropping through the pump like this. So let's just say this is 78%, and as we move further out, 71%, 58%. As you move further and further out, your efficiency lines are going to be less and less. If I could operate right here on this pump curve, that would be, I'm on my maximum impeller trim, that could be my best efficiency point. I can't get any more efficient than that point right there. And with this pump, let's just say it's about 83% efficient. As I move further and further away from my best efficiency point, I'm going to be less efficient. Just like I mentioned down here, if I put in smaller pump curves, notice that I can no longer get to. If I'm down here with a 4 3/4 inch trim, my impeller has been cut down. I've taken all that metal off, and now I've got all those open spaces. The maximum efficiency I could be here is maybe 62% efficient. Not very efficient. So we want to be careful, especially, I see this all the time when I'm working with engineers. Engineers will tell me, well, I never want to put an impeller in this pump that's at the full trim. I don't want to select a pump where I'm operating here. I want to put in a pump where I'm operating on a curve that's been trimmed. Their explanation to me is, well, what if I made a mistake? I can't take this impeller out and put a bigger impeller in to give me more head pressure or to give me more flow rate because the pump can't hold it. I'm limited. And that's a valid argument. My comeback to that is, well, just make sure that you're doing your engineering right. If you can, you want the pump to operate on this maximum curve because it's going to be the most efficient curve. I'd much rather operate on this curve than this curve or this curve or this curve because I'm going to be more efficient. Okay? So that's what we're looking at with our efficiency lines. When you look at this curve, their efficiency, their best efficiency point is approximately 80%. So it's marked there at 79.5 if I'm at my best efficiency point on my maximum trim. But on my minimum trim, my best efficiency is probably going to be close to 66%. So there's not much that we can do if we're going to trim that down because we've just opened up that space way too much. Now, we're going to talk about this when we get into part 2 of the webinar series. But when we use VFDs, a VFD, as it slows that pump down, it's just like trimming that impeller. If I slow that pump down in speed, I'm rotating on a different impeller line. The difference is I didn't shave all that metal off, so I don't have water just doing what it wants to out here. So it's like trimming my impeller, but keeping the same efficiency. Yeah, try that one on. The other nice thing about that is I can untrim the impeller by speeding it back up. I can operate on my 7 1/4 inch curve. I can operate all the way down here to my 4 3/4 inch curve and anywhere between or even lower by slowing my pump down. However, I can untrim that too and go back up to my full size curve, my full speed, by speeding that back up. You can't do that when you trim an impeller. The energy code, ASHRAE standard 90.1, actually comes in and tells you that if you don't have a VFD, then you have to trim your impeller so that you're not wasting energy by closing that discharge valve after your pump by throttling that back and eating up all that extra pressure. Again, we spent a lot more time talking about that in other classes. But instead of doing that, they say, well, you have to trim the impeller to get you to where you want to be. But if you use a VFD, you don't have to because that VFD will slow you down and will not waste the energy. In fact, it will save a whole lot of energy. So that's how we read the efficiencies. Let's take a look at that motor. We'll grab this blue one, and our motor curves are coming in like this. So in this pump, this might be a 3 horsepower, 5 horsepower, 7.5 horsepower, and 10 horsepower. And depending, so if we're operating at this best efficiency point right here, I'm in between 7.5 and 10 horsepower. Now these are the actual horsepower lines. So if I'm operating right here, I'm not 10 horsepower, I'm not 7.5 horsepower. The amount of energy that I'm using at this point would be considered my brake horsepower right at that point, at my point of operation. Well, we've got formulas that are on our website that you can use to actually calculate this point based on your flow, your pressure, and the specific gravity of your fluid. You can determine your brake horsepower energy and the water horsepower energy. But since we don't have time in this class, we won't discuss that. But you could look at this and say, well, I'm approximately 9. Approximately 9 horsepower, brake horsepower at that point of operation. So that's what we're looking at. I do not overload. My motor, my pump curve never really crosses 10, but I couldn't put a 7.5 horsepower motor on there, or 7.5, because if I did, I would overload that just for my point of operation. I could put a 10 horsepower, and I would be just fine for that point of operation. If I'm operating way down here, on this curve, that's being drawn right here, if I'm operating at that point, then I don't want to use a 3 horsepower because I would overload that. But I could use a 5 horsepower. A 5 horsepower looks pretty good. But at some point, I cross that 5 horsepower and I start to approach my 7.5 horsepower. So this pump curve will overload a 5 horsepower motor at a certain flow rate. Once we hit a certain flow rate, then we're going to start to overload that motor. So when engineers are selecting pumps, they look at this quite often. And unfortunately, I believe too many engineers always pick a motor that's non-overloading across the entire pump curve. So if an engineer were to pick this pump or this motor, he would size a 7.5. When in reality, when we look at the realistic application, they'll never exceed this 5 horsepower. Now you can't use that as a blanket statement, but it's fairly safe to assume depending on the difference here. And we'll talk about that more in just a little bit. So looking back on their pump curve, you can see their horsepower lines coming in. You've got your 1 horsepower all the way up to your 5 horsepower and your different points. And then last but not least is that NPSH-R curve at the bottom. Some pump manufacturers will show it a little bit different. Let's use a light green here. That NPSH-R is showing something like that. And then they've got the numbers listed over here. So as I have more and more water traveling through that pump, notice that my NPSH curve goes up as my flow across the bottom gets more and more and more. The more flow I have moving through that pump, what's happening is as it flows through these orifices in the pump don't change. As more and more flow is being flown through that orifice, it creates a larger vacuum. And as we create a vacuum at this point, we could create a large enough vacuum that we now start to boil the water. I have seen 85-degree cooling tower water boil and kill a pump because it's been cavitating. Because I've got so much flow that my NPSH-R, we'll write that up here, NPSH-R. There's 2 types of NPSH. This stands for net positive suction head. My NPSH-R and my NPSH-A. The pump curves will show you the NPSH-R. The R stands for required. My net positive suction head that the pump requires. This is the net positive suction head that's available. If I have more suction head available than what I'm requiring, then my water won't boil. Then we're good. However, if my R is greater than A, if what's required, so let's say this is, I need 20 feet of net positive suction head based on this pump curve. But when I run my calculations, I only have 15 feet. It doesn't matter what that water temperature is, it will be boiling. It could be 50-degree water for all I care. It is now boiling because that's all figured into this calculation. Now we do teach other classes on NPSH, so we don't have time to go over these formulas, but it's important to understand that's what we're looking at here. When you use pump selection software, you can put in, I've calculated 15 feet available, give me a pump that does not have any more than 15 feet required. When we select pumps off of pump curves, going back to their pump curve, you want to make sure that as you determine the flow rate through that pump, that your NPSH-R is going to be less than your net positive suction head available. So still looking at this curve, let's plot a point. Let's say that I'm operating 200 gallons per minute at 40 feet of head. So down across the x-axis is my gallons per minute, my flow rate. Up across the y-axis is my total feet of head. You notice that we are sitting in between the 7¼ inch diameter impeller and the 5 7/8 inch diameter impeller. So what impeller trim are we going to use? Well, again, based on that 1/8 inch increment, we could determine what that trim would be. So just eyeballing this, I'm about a half there and maybe one more half. So, you know, you might be somewhere around 6 3/4 of a diameter, maybe 6 7/8 of a diameter trim. You're going to be somewhere there. So that's what the manufacturer is going to trim that impeller down to if you don't tell them otherwise. They'll trim that impeller down to that size, and then we could draw a line, and we'll do that up here on the board. This is the 7 1/4. This is my 4 3/4, and this was my 5 and I believe it was 5 7/8. Yep, 5 7/8. And we're sitting here at 200 gallons per minute at 40 feet of head. So we could then look at this point and we could follow the same characteristics of these other curves, and right where we intersect here would tell us what our trim would be. And so we're just going to say that we are 6 3/4 inch trim. So that's what we would get. And now we're going to operate on this curve, not these other curves. So that's how we would look at that pump curve. My brake horsepower on this curve, well, we're in between 2 horsepower and 3 horsepower, but we're a little closer to 3 horsepower. So we could estimate maybe 2 3/4, 2.75 brake horsepower at that point of operation. We could look at our efficiency curves. Our efficiency, we're in between 75 and 79.5, so we could say we're probably close to 77. We're 77% efficient. And then last but not least, on this pump curve, we could look at our NPSHR, and we are sitting there real close to that 10 feet. Let's just say that we need 10 feet required. 10 feet of NPSHR. Now, to really make this NPSHR work for us, we would have to calculate our NPSHA. Now, I'll tell you this right now. Most closed-loop hydronic systems that are closed to the atmosphere, they're pressured to some given pressure, maybe up to 12 psi for a single or 2-story building. We get into a high-rise. This high-rise might be 20 stories tall. You're going to have a lot more pressure. We're going to have so much pressure in these closed systems that when we calculate our NPSHA, you're going to have so much more suction head available. Typically, this becomes a concern when we're pumping off of a cooling tower. If I have a cooling tower here, and this is open to the atmosphere, and we're pulling the water off through a pump, through the system, and then back to the cooling tower, it's all open to atmosphere. My suction pressure is only from the top of my liquid column to the suction of my pump. That's not a lot of distance. Plus, I might have some suction diffusers, I might have a strainer, something before that pump that's going to decrease the pressure drop to get there, so I'm losing my, that's where I see 85-degree cooling tower boil all the time. So we have to be careful. When we're pumping in an open loop system, then we have to look at the NPSHA available. And again, we teach you in other classes. In fact, we've got tools on our website that will assist you in calculating your NPSHA simply by entering the conditions of your application. So we've learned a lot from this pump curve. By knowing what flow we want, by knowing my pressure that we want, we can understand these other values. The other important thing to note here is that my pump curve, this shows a 1760 RPM. Now, it's not, I have a motor that's operating at 1800 RPM. And as we move higher and higher to more premium efficient motors, we see less losses. Back in years ago, we didn't even get to 1760. You might look at older pump curves that might be 1700, 1720, 1740 RPM. And this is losses because of the inefficiencies of the motor and the drive assembly. So, but this is operating at 1760. So this pump curve, my pump will operate like this on this curve as long as I'm rotating at 1760 RPM with the 1800 RPM motor. Now you put a premium efficient motor on there, and you won't be operating quite there anymore. It's going to be a little bit more efficient because you've got a premium efficient. If you have a standard efficiency motor, then it might be here. So again, this is not an exact science what they've done. They're not giving you all of the variables in this pump curve. But what we need to understand is this will be the minimum based on that standard efficiency or the EPACT efficiency motors, and then we will operate on this curve as long as we are rotating at that given speed. If my speed changes, so does my curve. And we'll spend more time talking about that in part 2 of the webinar series. Okay, what I'd like to do for the last part of this webinar is I'd like to go to the website to www.pattersonpumps.com, and we're going to use their pump selection software to select a few pumps. We're going to plug in some different conditions for these pumps, and then I want to compare some different curves and just make you feel more comfortable with the pump curve. I have been in the pump industry for many, many, many years. I've sold lots of different pump manufacturers. And I will tell you that I've been impressed with Patterson's selection software. It's a good software. It gives you a real quick bird's eye view of the curve so you can do a quick comparison. And it allows you to sort based on the efficiencies or based on the size, whatever you're looking for in that pump. First of all, we're going to visit www.pattersonpumps.com. And on that front page, you can see the little icon called Pump Finder. If we click on Pump Finder, it now brings up a couple of different pump selection programs. Now, Patterson Pumps is not just, as we all know, they're not just in the HVAC marketplace. But we want to make sure that as we pick this selection software that we pick the correct one. So we want to find the one that's for the HVAC applications. So looking at these different pump selection software programs that are here, we would want to select the PHD, the HVAC Pump Selection Program. And once we select that, it will take us to the login screen here. Now what I've done is I've made this login screen a favorites so that I don't have to go through the steps that we just showed you. I click on my favorite and it takes me instantly to where I want to be. And once we're here, you type in your username and password. If you don't already have a username and password, follow the procedure here. It will contact Patterson Pumps, and they will get you that username and password established for you. So I go ahead and enter mine, and we'll log in. Once we're logged in, we can click on Start the Pump Selection, and this will load the selection program. Once we're in the selection program, it starts us off with the flow rate. We can change the type of flow rate and the type of head that we're measuring, but for this application we're going to leave it to US gallons per minute and to measurements of the total head in feet. Let's pick an application, or let's select a pump for an application for 750 gallons per minute at 55 feet of head. Now, before we do anything else, there are some other conditions that we need to look at. We can tell it whether or not we want to be left of best efficiency point or right of best efficiency point. Now, when we talk about left of best efficiency point or right of best efficiency point, again, we're looking at these efficiency curves that drop in like this. Now, I am operating right here. I'm at my my best efficiency point would be right here, so I'm a little bit to the left of that. When we select pumps, we need to consider where do we select a pump? Because I could pick a pump on this curve that's out over here. Or, where we're only doing 100 gallons per minute at, say, 35 feet of head. I would be operating out over here. I am well on the best efficiency point here would be right at this point. So I'm well left of that point. I could select a pump out over here that's doing 275 gallons per minute at 28 feet of head. Where do I want to pick my pump curves? We need to limit ourselves on where we select because this is way out to the right and this is getting way back to the left. Well, ASHRAE gives us some recommendations of where we should select our pumps. First of all, they tell us a window that looks something like, here's my best efficiency point, so something that kind of looks like that. This is a good selection range. You want to pick something within this range. That is 66% to 115% of our best efficiency point. So if my best efficiency point is right here, then I can be 15% greater than or 34% less than my best efficiency point. So that gives you a good guideline of where you should try to select these pumps. Now, there are times where we just simply can't because our condition's too crazy and we don't have pumps to match it. But when we have that option, we'd want, where we're picking multiple pumps, that's where we'd want to focus. And we'll talk about that when we look at some of these pump curves. So we can tell this program that we could select to the left or to the right. Typically, you'd want to select to the left because, and the reason that ASHRAE allows us to do this is engineers are putting safety factors on their head values. So they calculated 25 feet of head, but they put at about 20% safety factor on it. Well, 20% of this would be an additional 5 feet. So now they're going to size their pump, for 30 feet of head. Well, in reality, they don't have 30 feet of head. They only have 25 feet of head. And what's that going to do on the pump curve? Instead of operating, we'll draw a new pump curve right here. Yeah, I guess we could do it on here. Instead of operating here, they could operate out over here. So what it does is it could pull them closer to best efficiency point. But if they selected the pump out over here and then they lost their head pressure, it takes them further away from their best efficiency point. So that's why ASHRAE gives us more leniency to the left, because with the safety factors that are being used, it will pull us back, in reality, back towards a higher efficiency point, not further away from. So if you're going to do best efficiency point, it might be best to select that of left of best efficiency only. But honestly, I don't even do that, because I want to look at all the pumps that are available. The near miss, you can plug in what percentage you want of your head and how close that can be. The fluid in NPSH, right now it defaults to 60-degree water, but I'd like to change that because I'm here in Salt Lake City, Utah, and I've got some pretty cold design temperatures. So we're going to select a fluid from the list. If you're pumping some special syrup or something else that you want to plug in some properties for, you could do that with the custom fluid properties. But we're going to drop down this arrow and we're going to find 40% propylene glycol. Now the temperature, as I mentioned before, the temperature is critical with your glycol. The temperature, the colder your glycol solution, the more viscous it becomes. The hotter it is, the more likely it is towards the conditions of water. So let's change this temperature. It's a hot water heating system, so let's, the coldest it will ever operate typically is maybe 100 degrees. And we'll save that, and now that plugs in, that changes the properties of our fluid. Now we can select the type of pump. We can select a circulator pump. We can select a horizontal split case pump. We can select their HVES, which is their horizontal end suction pump, or the horizontal end suction pump closed coupled, or the vertical inline pump. So those are the options that we're given. Typically, we will know what type of pump we want. We don't talk about that in this class, but we do have some other classes where we talk about the advantages and disadvantages of each type of pump and when we should consider a horizontal split case instead of a horizontal end suction, or when we should consider a vertical inline instead of a horizontal end suction. So these are, again, we talk about that elsewhere. But let's say we want to pick this HVES-CC. And actually, I want to look at both, the HVES-CC and the HVES. So to select both, you have to hold down the Shift key or the Control key, hold down the Control, click on HVES and the HVES-C. Speeds. What kind of speed do I want? Do I want a high rotating speed? Well, typically that's going to be noisy. Do I want a low rotating speed at 1200? Well, that's going to take the cost of our motors and take it up. So I'm going to try to keep it at 1800 RPM. So I'm going to select 1800 RPM and leave it at that. Getting into the motors, do we want a standard motor? Well, I just usually leave that to the manufacturer's specification. What kind of enclosure do we need? If we know we need something different like a TEFC, whether we want an open drip proof or a TEFC. Again, keep in mind that if it's an outdoor motor exposed to the outdoor elements, it better be the TEFC or the total enclosed fan-cooled motors. If it's an ODP or inside, then it can be the ODP or the open drip proof. So we'll leave that to the manufacturer's spec. And then the sizing of the motor. This is kind of going back to what we talked about before. Do we size the motor for that point, that operating point, or do we size it so it's non-overloading across the entire pump curve? Or do we not have the program size the motor at all? So we've got all of these options. Let's have it selected for, just for this application, maximum power on the design curve. We could have it select for the maximum power on the maximum diameter. That's going to give it the biggest motor that pump would ever use. Well, we're going to do the max power on design curve. We're only interested for what our curve requires. So now we've got all of this plugged in. We know we're going to be picking a horizontal end suction pump, whether it's split coupled or close coupled, we'll determine that, and with these conditions. So now we click the search button. Now this is a beautiful, beautiful screen here, because this gives us a bird's eye view of what we look like on our curves. And you can see where our operating point falls with that first pump, that E6V9A. That is going to be a little bit to the left of best efficiency point. Now it looks like we're probably within that 66% of best efficiency point, so that could be a good pump. Typically this thing will start with sorting based on the efficiencies. So you'll notice the first pump that's up is 80% efficient. And as we drop down, the efficiencies will also drop down as we continue to go down this list. We've got quite a few options available to us. Well, if I compare that first pump on the first line to the pump that's down here on the 5th line, you'll notice the one on the 5th line is operating much closer, probably right at or very close to my best efficiency point. So that could be a great selection. But you also notice that I'm only operating at 77.8% efficiency. So I'm actually, even though I'm at my best efficiency point, I'm actually less efficient than I was with the pump that's operating to the left. Why? Because it's a smaller pump. Notice that I'm now dealing with a 5x4, 5-inch suction by 4-inch discharge, and the pump up above is an 8-inch suction and a 6-inch discharge. The larger your pumps go, the better your efficiencies can be. The question is, should I go with the closed coupled or should I go with the flex coupled? Well, I'm looking over here at the motor sizes, and with the bigger pump I'm looking at 20 horsepower, the smaller pump I'm looking at 15 horsepower. What would I suggest? Well, again, we talk about this in another class, but I would suggest a flexible coupled or a split coupled pump, because I don't want to be that maintenance guy who's got to change that mechanical seal or trim the impeller or change the bearings and have to do that by taking that big 15 horsepower or 20 horsepower motor off. I don't want to have to lift that. I don't want to have to deal with that. If I have a split coupled pump, then all I have to do is break the coupling, and I can pull the pump shaft out without even touching that motor. So because of the size of the motor, I would go with a flex coupled pump. If this were a 3 horsepower, 5 horsepower, maybe 7.5 horsepower, then I would consider the closed coupled. So I'm not going to even consider the closed coupled anymore. So I'm going to look at the E4P9A-1 or the E6V9A-2. I think those are going to be my two best selections. One is going to be more efficient. The other one is going to be less efficient. However, where do we sit? Notice that if I go with the larger pump, it's telling me I need a 20 horsepower motor. If I go with a smaller pump, I can use a 15 horsepower motor. Let's understand why. Let's look at the curve for the larger pump. If we look at the brake horsepower, or try to estimate what the brake horsepower is with this pump, we're sitting just under 15. So I don't even need, I could get away with the 15 horsepower. But when I hit approximately 900 gallons per minute, then I'm going to start to overload that 15 horsepower motor. Now, as I continue down my pump curve, at the very end of my pump curve, I'm actually back under 15 horsepower. But an engineer might look at this and say, well, I don't want to overload that 15 horsepower motor, so I'm going to put 20 horsepower on there. But when we look at it realistically, again, we don't have time to talk about this here, but that's telling me I've got to, instead of flowing 750 gallons per minute, I've got to flow 900 gallons per minute, and then I'll overload my pump or my motor. Well, if I take this pipe system that is sized and with so much pressure to give me 750 gallons per minute, if I now squeeze 900 gallons per minute through that same pipe size, my pressure is going to go up very, very fast. It's based on the affinity laws. Now, we do teach other classes on our website about the affinity laws, and it will help you understand that. But I'm expecting my flow rate to go up 150 gallons per minute. My pressure is going to go up a squared function of that change. It's going to be huge. There's no way this pump could even do that. There's no way that the system could take that, so there's no way you'll ever operate there. But a lot of engineers don't consider that, and they look at this and say, well, I want a 20 horsepower. When in reality, they probably will never even, unless they break the pipe somewhere and it's blowing out to atmosphere. But even with this pump, we're blowing out to atmosphere, it would pull us back down into the 15 horsepower line. So these are things that have to be evaluated. So the engineer might demand that you use a 20 horsepower, but we could get away with a 15 horsepower on this pump. So this pump could be good. We could still do 15 horsepower. We're not too far from our best efficiency point, and we are fairly efficient. The pump itself is going to be bigger, and it's going to cost more. So these are things that we want to evaluate. If we go back, let's look at the curve of the smaller pump. Instead of 8x6, let's go 5x4. We've really cut our size down. Now we're just barely to the left of the best efficiency, or to the right of best efficiency point. And my brake horsepower is about the same. Of course it's going to be the same. It's going to be very close because the efficiencies are close, and it's still moving the same amount of water at the same amount of pressure. And based on the formulas that you can find on our website and in other classes we teach you that, of course, that's what generates that water horsepower, is the amount of energy to move water at a distance. So the horsepower is about the same, but this curve never goes over 15 horsepower, so the program has selected a 15 horsepower. So again, that helps us in our selection to decide what to do. This pump looks good. It's slightly less efficient than the other pump, but it is smaller. So now these are things that you have to evaluate. Do you want the higher efficiency and pay for that bigger pump? It looked good on the curve. Or do you want to save the money on the pump, get a smaller pump, and have it operate slightly less efficient? These are things that have to be evaluated. The reason this pump is further out to the right is because it's got smaller connections. It's only a 5x4. You go into a larger pump and it's going to pull you further to the left. This pump is slightly to the right. The bigger pump is slightly to the left. That means that we have a bigger pump for the application. Here we have a smaller pump for that application. Now the nice thing, so that if you don't want to estimate on your brake horsepower, if you click up here on printed reports and go to the pump data sheet, you could fill in the company, the name, the additional information, or just submit it as is. This will give you all the details that you'll ever need for this pump. With this data sheet, it gives us all the information about our pump, the rotating speed, the size of the diameter, the trim of the impeller, and then down along the left-hand side here, it gives us our power, our brake horsepower at that point. So we are 13.8 brake horsepower. Our efficiency is 77.8 at that point. Our NPSHR, instead of trying to guess based on the lines, it tells us it's 11.2 feet. It tells us what our shutoff head is. The shutoff head is that head pressure, back to this curve. If I were to close the discharge valve on my pump has zero flow. It's operating at full speed. So zero flow on this curve at full speed. I know what my impeller trim is. That's my shutoff head. So my shutoff head would be 72.9 feet. And then it gives us our minimum flow rate. Minimum flow rate is very important when we get into systems that are operating with two-way control valves. And we actually talk about that in other classes. So there's a lot of valuable information that we're given here. And because we use 40% propylene glycol, we go over to the fluid, and it gives us our specific gravity, our viscosity. Information that's important as we plot some of this pump information. So hopefully that helps you understand how to select a pump. Hopefully we've opened your eyes a little bit on how to use the Patterson pump selection software. It's a good program. It gives you some really good information on the pumps that you're using. And quite honestly, I use it all the time when I'm selecting pumps for different applications, when I'm working with different people across North America. Again, I appreciate the time that you've given me here for the past hour, and certainly I hope I've made your jobs as HVAC professionals easier when it comes to HVAC pumping for your hydronic heating or cooling applications. Hopefully we'll see you around our website. Hopefully we'll see you around some of our other training classes, and you can always submit your questions or comments to us online. Again, visit us at www.pipelinedevco.com. We've got all sorts of online sizing tools. We've got many different webinars, and we're always putting out new webinars. We've got lists of webinars that we have intentions to put out in the future. And there's a great community discussion forum where you can get on and ask questions and interact with other members, other HVAC professionals across the world. So again, we appreciate the time, and hope to see you next time. Thanks.